I don't know how far the range of sound gets. Anywho, we know this harmonic series is a divergent series. Even though the terms go to 0, they don't do it fast enough, and the partial sums grow without bound. Okay, so that's just a refresher. But there's sort of an interesting thing that'll happen, and what we're going to look at today is called alternating series. So series that has terms that alternate between positive or negative. So they're either of the form -1 to the k plus 1, just meaning we start positive, then negative, then positive, then negative, or -1 to the k, start negative, then positive, blah, blah, blah. So yeah, if we look at like the alternating harmonic series, written as follows, our terms would be 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, so on, so forth. Now we knew that the regular harmonic series is divergent. But let's explore whether the alternating harmonic series perhaps converges. And so we're going to plot a graph of the partial sums. So the first sum sub 1, S sub 1 I'll write under here because this is supposed to represent sum sub whatever. Okay. It's just 1. So our first sum is just one term, which is just 1. Our second sum is 1 minus a half, which is equal to a half. Okay. So we go down because we take our thing and then we do minus a half. Here we started at 1. Our next sum is a half plus a third, which I think is 5/6, but the details are less important than showing what's going on here. So here we're going to add a third. Then we're going to take whatever value that was, in this case 5/6, but pretty soon I'm not going to figure out what fraction it is, and we're going to subtract 1/4. So we're going to go down by a fourth. And we'll land somewhere. Next, we take our current partial sum and then we just add the next term, which is a fifth. So let's suppose a fifth is this. And then we're going to add our next term, which is actually subtracting a sixth. And then our next term tells us we must add a seventh. We end up here. And so on, so forth. Right, and I've run out of space. But I want you to talk in your groups. What do you notice is happening to the sequence of partial sums, S sub n? What is happening? And do you think that that means that we will converge or that we will still diverge? So take a moment to discuss in your groups.
It's convergent. I don't know. What does this look like? It's gonna be like something like
What do we notice? What do we think is happening here? What is the deal? What's the dealio? Yes?
Their convergence.
Okay, it's convergent. Now, how would you justify such an argument? Why do you think it converges?
Because they're going towards a specific value.
What value?
Some value between 1 and 0.5.
Okay, I agree with that fact. How can we be so confident that it'll approach something or that we're getting convergent? What's basically happening here? Yeah?
You're subtracting a term, but then you never undo it because the term you're adding is smaller.
Yes, excellent. That's exactly it. Each step cannot be undone because whatever we did first, like minus a half, we can never get out of that. We can't get beyond that again because we add a third. And then the next thing we do is less than a third. We subtract less, and then add less, and then subtract less, and add less, and subtract less, and add less. So I think of it as we're sort of getting ourselves trapped into an ever-decreasing channel. We can never get back to where we've previously been. So like, we sort of get trapped and get smaller and smaller and smaller changes as we go along. So we seem to get trapped and approach some limit. And that is the case, and we will not prove that fact rigorously at all. But this is the idea behind why an alternating harmonic series converges. Even though the harmonic series normally diverges, this alternating behavior traps you in this channel, and you converge. Okay? So I like to say you get trapped in a channel. Okay. That is the essential idea behind it. Just out of curiosity, I'll Google what the alternating harmonic series converges to. Converges to. Ha. The alternating harmonic series converges to ln2.
What is that?
So the limit is natural log of 2 is what we happen to converge to. We'll be able to prove that later, I think. But for now, I think we need integrals. Anywho. So that brings us to what's called the alternating series test for convergence. So if we have some alternating series characterized by -1 or some alternating piece.
We are telescoping series alternating or no?
Uh,
Because like, don't they have the negative positive thing?
Yeah, the slight difference is that like this is defined as like the negative part can just sort of sit on its own, and then the series part kind of lives out here. So you might be able to rewrite it. I don't know. I'd have to think about it more. But the real characteristic we're looking for is that you could rewrite this completely positive or like positive negative. Like you can do it both ways. But you may be right. I don't know. Okay. Will converge if two conditions are met. First of all, the limit as n goes to infinity of a sub n has to equal 0. This is logical. I mean, that's the nth term test anyways. So that has to be true. Our terms have to get, the magnitude of our terms have to get really small. And then there's a lot of words here, but the terms eventually have to be non-increasing. And I'll elaborate on that in example 3. But basically that's just saying the distance from 0 for each term has to get smaller and smaller and smaller and smaller. Which I guess kind of makes sense. You have to not be able to get back. You have to stay trapped in that channel. Any questions about any of this before we do an example? Okay. It's really just about being trapped in that channel, and then you just show these two criteria. So in example 1, criteria 1, we take the limit as n goes to infinity. Now this is one little notable thing that you might not notice in the notation. This a sub n part ignores the -1 to the whatever part. It's just saying of the positive version or of the regular version, the nth term test has to hold. So we don't pay attention to the -1 to the whatever. We just say this over 1 over square root n is equal to 0. Check.
So is a to the n, is a n a k?
Yes. Yeah. The switching between these n's and k's, I'm probably a little inconsistent in it, and it doesn't really matter. But yes. So by itself, the 1 over square root something will go to 0. And then the second thing that we need to show is that the terms are strictly non-increasing. Again, we don't look at this. Like in this, I wrote absolute value, but you don't actually need it. We're technically just looking at the part that it does not include the negative part. So if you want to think about it as being absolute value, maybe that helps to remind you it's positive. That's why I wrote it in. But strictly speaking, you're just comparing the part that's not with the -1. So we just need to show that 1 over root k is always less than or equal to 1 over root k plus 1. Okay. We need to show that the terms never increase, or at least eventually never increase. Other way? Yeah, so true. Thank you. Okay, and then that's easy to do. This is more or less a comparison test. We can say root k plus 1 is greater than or equal to root k. We can square both sides. K plus 1 is greater than or equal to k. Subtract k from both sides. 1 is greater than 0. This is true for all k. Okay. Therefore, we converge by the alternating series test. Okay. So you just have to show these two criteria. We show that it is strictly non-increasing at some point, and we show that the nth term goes to 0. Relatively easy. Questions? So carrying out the test is great. The thing I really want you to understand is like the reason is because we get trapped in a channel and we just can't get out of that channel. Example 2, show that we converge. So we're going to take the limit as n goes to infinity of 1 over n plus 1 factorial. Okay. We ignore the negative 1 to the k part. And that is just equal to 0. So we satisfy our first criteria. Second criteria, we have to show that we're decreasing, so 1 over k plus 1 factorial. The next term is supposed to be less, so we can say 1 over k plus 2 factorial. I will cross multiply here. Because we are not dealing with any negative terms, like these things would be positive, we're ignoring the negative part, we can multiply across the inequality without fear. So we can say k plus 2 factorial. Actually, I'm not even going to cross multiply. Let's just do it like this. Times k plus 2 factorial and k plus 2 factorial. You can cross, I mean, it doesn't really make a difference. How can I rewrite k plus 2 factorial? Very good. K plus 2 times k plus 1 factorial all over k plus 1 factorial. And these things cancel. And we are left simply with k plus 2 is greater than or equal to 1. This is true for all k greater than or equal to negative 1, which is sufficient for our criteria. So criteria 2 is met, and then we can say this is convergent by the alternating series test.
So why is that? Why specifically -1?
So then k actually is positive.
So k just has to be greater than or equal to some natural number. I mean, I guess negative 1's not a natural number, but like it's also true then.
0 or 1.
Yeah, like you could pick k is greater than or equal to 1. So you could say that if it feels better.
Prove it's convergent just has to be greater than some natural number.
Yeah, because you're basically saying once you hit some natural number, forevermore, it will always be greater. Okay. All right, questions?
Wait, how do you go from k is greater than -1 to k is greater than?
So k
Mm,
can't be like.
I don't know. They're just equivalent expressions. You don't have to. I don't think you have to say that. Cam was just saying since negative 1's not technically a
Wait, why
negative
would it be
1.
1? I thought the
I
k.
was just
I
thinking,
thought the k could
I've been
equal
confused about like if k
Oh,
is
no,
greater
But
than
if you like divided by a negative number, would that flip?
Nah, we're not going to divide by a negative. You're just saying if k is greater than or equal to negative 1, k is also greater than or equal to 1. Like if it's true for this, it's also true for this.
Yeah, okay.
That's all we're saying.
Oh, okay.
Yeah. All right, last bit. So why is criteria 2 necessary? Why do the terms have to be strictly decreasing? We're going to consider a piecewise defined sequence, A sub n. And then we'll look at the alternating series built with that piecewise defined. So if we write out the first several terms of this series, term number 1, we're starting on a positive, negative 1 to the 1 minus 1. So it is positive when it is 1 and is odd, so it is 1 over 1. Our second term is going to be negative and is even, so it's 1 over n squared. 1 over 2 squared is 1 over 4. Next, third term, odd, 1 over 3. Fourth term, even, 1 over 4 squared is 16. Next term, odd, 1 over 5. Next term, even, 1 over 6 squared, 1 over 36. And we're going to do this forever. We still meet the first criteria, no problem. The limit as n goes to infinity, regardless of whether we're odd or even, both are going to 0. So it is 0. But if we plot the partial sums here, and I'm going to just pick an arbitrary location for 1, maybe I'll say it's right here. So we start at 1. We go down by 1/4, and we land at 3/4. But what are we now going up by? 1/3. So we're not stuck in a channel. Then we go down by 1/16, not much at all. And then what do we go up by? 1/5. And so we continually break out of this channel. So that's why we need that criteria that the terms must be strictly non-increasing. Okay. Then we go down by some teeny tiny amount. And we go right here. And then we go up by some slightly less tiny amount. So over time, we're going to keep growing and growing and growing. So are we going to converge? No. The understanding is all about the 2 graphs, I think. Thinking about whether you get trapped in a little boundary or if you can get out of the boundary. The criteria in the test is very simple to do. Questions? All right, you got time to head start your homework.